Okay, so a very good morning. Today we will be talking about integer linear programming, or we call it ILP. Okay, so as the name suggests, it is an LP, okay, in which some or all of the variables are required to be non-negative integers. Okay, now what does integer variables do? They allow you to build more accurate models for a lot of common business problems. Okay. So, for example, there can be a lot of real life issues which you might be facing, and you have to choose an option in their structure. Okay. So, like some of the examples are, let's say, which stock to invest in. Okay. Or maybe which supplier or vendor you have to select to get your work done. Okay. So many of the decisions and variables in real life scenarios, if you see, they are completely inherently integers. Okay, so some of the examples are, for example, you have to do scheduling of employees or machines. Then let's say timetabling, then production planning and scheduling, or investment, okay, or project selection, or bin packing. So all of these are your various kinds of real life scenarios where you have to use ILP. Okay. Now there are three types of ILP models. Okay. So the first one is, we call it pure ILP. So what is pure ILP? LP in which all the variables, okay, all of them are restricted to be integers only. Okay. That is your pure ILP. Okay. So for example, if I say that, let's say some function, okay, your max z is equal to 3x1 plus 2x2 subject to x1 plus x2 less than equal to 5. Okay. And x1 and x2 are greater than equal to 0. And x1 and x2 are positive integers. Okay. Then that is a pure ILP. The second one is a mixed ILP. So in mixed ILP, only a subset of variables are restricted to be integers. Okay. So let's say the same model you have now, but I say that, okay, only x1 is an integer. Then that is a mixed ILP. Okay. And the third category is 0, 1 ILP. Okay, so this I'll just write it. This is your mixed ILP. 0, 1 ILP means you have binary variables. What are they? Whose
Yes.
values are, yeah, tell me.
Yes, ma'am. The answers must be in 0 or 1. Like,
Decision variables. Okay,
yes,
don't say
ma'am.
the answer, right? So the problem
Yes.
then is called a 0, 1 ILP. Okay, so let's say the same model, max z, subject to, okay, x1, x2 have to be non-negative, and x1 this way, right? Got it? So then that is your binary ILP. Okay. Now, MIL, MILP, okay, we also call this MILP. They are usually much harder to solve than ordinary LPs. Can you tell me why?
So what's the question?
Why are, okay, I'll just write it. Why are MILPs much harder to solve than ordinary LPs?
Why? Because I mean, some of the decision variables cannot take fractional values. Uh,
Right, absolutely right. Okay. So because of the inherent, yeah, I'll just ornament whatever you said. Because of the inherent combinatorial nature of the solution approaches, which are necessitated by integer variables. Okay. That makes MILPs pretty hard to solve. Okay. Because now, even if you have like a solution space, you cannot simply take up a solution from there. No. You have to ensure that that is also an integer. Okay. The next thing that we study about is called LP relaxation. Any idea or anything which hits your mind after hearing this?
so I mean, from the relaxation term, what I feel is that probably for some time we allow that okay, the fractional values are allowed for, I mean, instead of the integer ones.
Exactly. So LP relaxation is always obtained by omitting all integer or 0, 1 variables. Okay. So let's say if this is your model. If I have to do an LP relaxation of this, then it will be max Z. You know what is Z? Subject to, sorry, it's less than equal to. That's it. Okay. So you simply omit all the integer or the 0, 1 variables in your model. Okay. Now, these are some of the concepts. Okay. So I'm just writing so that you know why we are studying all this. The concepts. The second one is integer feasible versus LP feasible. Okay. So when you do an LP relaxation, okay, it is a less constrained or a more relaxed version of a normal integer linear programming model. Okay. So the feasible region for any ILP must be contained in the feasible region for a corresponding LP relaxation. Is that true? Do you resonate with what I just wrote?
Yes, yes, it's fine because
Absolutely, right?
yeah.
Because let's say, okay, so you have some values here, okay, and uh, let's say this is some solution space. Okay. So your integer feasible solution would look like somewhere here. You get it, right? So,
Yes, ma'am.
okay, like this, everything. All of these are your integer feasible solutions. Note, I'm calling it feasible, not optimal. Okay. So the next point which brings us is then how do you obtain an optimal solution? So the optimal solution to an LP relaxation will give you what? Can you tell me? It
So,
kind of
The
tells you that what will be the, yeah, tell me.
so, so,
optim
I mean, we'll give upper bound if it is a minimization problem, then this optimal solution will give, probably will give the upper bound of the solution.
If it is a maximization problem, then it is an upper bound. Okay, you are kind of right. So the optimal solution gives us a bound. Firstly, it gives us a bound to the objective function value. Okay, so for a maximization problem, the original, not original, the optimal Z value of an LP relaxation for a max problem, I repeat, it is an upper bound to the optimal solution, to the ILP solution. Okay, very straightforward, very intuitive. So similarly, for a minimization problem, the optimal Z value of LP relaxation would be lesser than that, lesser than the optimal Z value of ILP. So for a minimization problem, the optimal Z value of an LP relaxation would serve as a lower bound to the Z value. Okay, Z value of an ILP. Okay, now the third thing which we read, and I think most of you must know this because I guess somewhere I had probably discussed. So if you have to solve ILP problems, so up till this is clear to all of you, right? No doubts, nothing.
Yes, yes, clear.
Okay.
That's clear.
So when solving an LP relaxation, okay, sometimes you get lucky and you obtain an integer basic feasible solution. So do you remember what we mean by modularity, unimodularity? Had I discussed it?
I don't remember that we discussed it.
Okay, fine, no problem. So if your ILP has the form of max an objective function such that AX is equal to B. See, usually using AX equal to B only, you represent all your constraints, right? You have something called A11, X1 plus A12, X2 plus dot 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 dot. Some AN, A, let's say 1N, okay? Xn less than equal to some value. So like this, you will have certain constraints. So you can simply put X1, X2, Xn here, and here you can put the A values, and here you can put your B values. So this is what I mean by AX is equal to B, right? So A is also known as the, just for your information, it is also called the technological coefficient matrix, okay? So such that Ax equal to B where A and B have all integer entries and A is totally unimodular, then every BFS is integral. And if every basic feasible solution is integral, then consequently the solution obtained by the LP solution method would be integral. What I mean by this is that if the structure of your problem is such that A and B have all integer entries and the matrix A is totally unimodular, then even if you solve your ILP using normal simplex or any other solution approach of LP, then you will be getting an integral solution. Okay. So what is unimodular? First, I will tell you what is unimodular. Okay. So unimodular is nothing but an integer m comma n, m cross n, not comma n, m cross n matrix, that is A, is unimodular if rank of this matrix is equal to m and every m cross m square submatrix of order m of A has a determinant value of -1, +1 or 0. Mostly even if, okay, just give me 1 second. So mostly even if this requirement is met, usually they call that, okay, my matrix is totally unimodular. Okay, so this is called unimodular. The only variant is when we call it totally unimodular is that you don't have to look for the rank of A in this case. Okay, what happens here is that let's say every k by k square submatrix, okay, of order k of A has a determinant equal to -1, +1, or 0. Okay, where of course k has to be less than equal to minimum of m comma. Got it? So if every k cross A square submatrix of A has a determinant value of +1, -1, or 0, if you have to simplify this and just remember, then in that case, your matrix is totally unimodular. Is that clear?
Yes, yeah.
Okay. So, totally unimodularity, if I have to give you an example, I think I had discussed it in the transportation problem only. How come you guys said you don't remember? In the transportation problem, once your matrix, let's say, has only ones or zeros, and one does not have to necessarily appear only once in one, I mean, once in one row, but it might be twice in column because you have the supply and the demand quantities. Then that is your totally unimodular property. And due to this totally unimodular structure, actually, you can solve the transportation problems also using your simplex or any other method. So this is one way of solving it. Okay. The other way is very tempting. It is rounding off, right? So it is very tempting to simply round a fractional solution to the closest integer, but this does not work reliably. Why? Because the rounded solution may be infeasible,
Yes, ma'am.
है ना? Or suboptimal. It's not a very good method. Okay, what are the other solution approaches? Any idea? Have you heard? So if I have to say that using graph, you have to obtain your solution, can you obtain, or do you need me to show it graphically also? Because graphically is very simple. You simply plug in the points. Okay, then you check for the integer ones, whichever are the integer variables lying in that region, and then you check that what is happening. Or do you want me to do it for you?
No, ma'am. Understood.
Understood, right? Complete enumeration you will do, so I don't want to waste my time explaining that. So, okay, you don't know the other solution approaches, I'll just write, no problem. So, other solution approaches are, we have pure ILP. For pure ILP, we have cutting plane algorithm, and very important, branch and bound method. Just 1 second, I'm just having a call. I'll just come back in a while. Okay, I am so sorry. Yeah. Then for what is happening? Okay, I think. Then for 01 ILP, okay, again you have like branch and bound. Then you have like Bala's additive algorithm. So I'm just noting all these down because even if I'm not able to cover them, you can always go back and check it, how it works. Then you have the Boolean algebra approach. Okay. And for mixed ILP, you have modified branch and bound. Okay. So do you have any idea about how does branch and bound work?
Yes, so I
Ma'am,
mean, we do some kind of pruning. I mean, at the level of the leaves, if we vaguely
Mm-hmm.
remember correctly. Yeah.
Okay, fine. So it is essentially a strategy of divide and conquer. Okay. So the idea is you partition the so much lag at times. This doesn't happen when I use iPad. It always happens here. So you partition the feasible region into more manageable subdivisions. Okay. And then if required, you further partition the subdivisions as well. Okay. So this is if required. So in general, there are a number of ways to divide the feasible region. And as a consequence, there are a number of branch and bound algorithms. So theoretically, this can solve any ILP. But practically, if you say, it takes a lot of computational effort. Okay. So for example, in cutting plane, what happens is, if you go, you can look it up on YouTube also in the cutting plane method. You add one constraint at a time till you get an optimal solution. But in branch and bound, if the current solution is not integer, then you split the problem into two subproblems with one constraint added to each. Okay, I'll just write it so that you remember also. So if the current solution is not integer, okay, then you split the problem into two problems with uh, one constraint added to each and then solve again. So you repeat till you get an integer optimal solution. So basically your BNB solver will use this approach. Okay. So if I have to give you an example, what happens is that you do LP relaxation of the problem. Okay. So, okay, let us find out an example to work with, I guess. Okay, maybe I will use this one. So let's say your thing is max 7x1 plus 11x2. subject to x1 plus x2. I hope this gives an integer optimal solution. 18x1 So this is what? This is an LP relaxation, as you can see, right? Because I know this is an ILP and I need to get an integer solution. Okay, so first you have this. So if I have to draw a graph, I go by the graphical method. So let's say here, so here you will have one constraint, right? For this one, you will have so how much is your x1 value if x2 is 0? Let's calculate. That is 154 divided by 18. So you have somewhere here. You're getting it, right?
Yes.
Somewhere here you will have, and that would be 154 divided by 34, somewhere here, 4.5. Okay. So you will have this. Okay. So here you are getting an intersection. Okay. Somewhere here. Actually, my bad. I mean, if you solve this, how much will you get? Let's see. You'll get 18x1 plus 18x2 is equal to 108, right? And 18x1 plus 34x2, you'll get 154. So if I do minus, then you're getting how much? Minus 16x2. Please ensure that I'm doing the calculation right. This will be minus 46. So some 46 divided by 16, that is x2 is your 2.875. This is 2.875, then x1 is 6 minus 2.875. So that is 3.125, right? So here you will be getting your optimal solution. Okay, so if I have to, if I have to do the demarcations correctly, and somewhere here should be your 2.875, and here is your 3. This is still okay, right? So this is your 3.125, 2.875. I'll just do the marking. So here was your 6, I think 6, 0, maybe 1, 2, 3 somewhere here, 4, 5. Okay. Sorry for my, and yeah, so your Z value would be 7x1. Can you calculate this and tell me what is your Z value? Plus 11x2. That is basically that is 53.5, right? So you first start with the LP solution. Now what do we do? Next thing is that we will make this as a root node. Okay. So Z is equal to 53.5. You got. Okay. Now I will, let's say, try to make this as an integer. So here is my root node. Okay. And I'll try to partition this problem like this. So here, on one hand, I will have x2 less than equal to 2. On one hand, I'll have x2 greater than equal to 3. So now these two individual problems become max z, okay, subject to your x1 plus x2 less than equal to 6, 18x1 plus 34x2 less than equal to 154, and again your x2 less than equal to 2. And now you try to solve this. So now if you try to solve this, let's say, see, this remains the same. I'll try to solve this on the same. Your x2 is less than equal to 2. That means the line would be somewhere here. Right? So your optimal, so mainly if I have to do this, then it's kind of like this becomes your feasible region now, isn't it? Because this is your, okay. So this is your x1 plus x2. This is your 18x1 plus 34x2 less than equal to 154 line. So basically it is, okay, I think I made a mistake. None of you pointed it out also in the demarcation. This is 6, right, guys? This is 6. This is somewhere, this is 4.5, right? So here you have 5, you will have 4, 3. It's fine only now. So here 18x1 plus 34x2, you have the region pointing like this, right? And then you also have this. Okay. So why we obtained here? Because it was the corner point. Because ultimately, initially, this was your feasible solution. And now after adding this constraint, this becomes your feasible solution. Clear?
Yes.
Yes.
So, what think? So when this becomes your feasible solution, then your corner points are here. This, and this. And if you check, mostly I think here only on 4,2 will you have a solution, because here it is 6,0. So that is 7 into 6. How much? 42. Here it is 0,2. So 11 to 22. And here it will be 4,2. So that is 7, 4, 28 plus 22. That is 50. So you will have now z equals 50 and 4, 2. So this is already feasible. So once this has become feasible, that means no need to expand this branch further. Okay. But here you still have one. Okay. So here is where you will be adding x2 greater than equal to 3. So when x2 becomes greater than equal to 3, if I have to do it on the same graph, so that means here. So then for x2 greater than 3, this becomes your feasible region, right? This was for, I will just write it, x2 less than equal to 2. And this is for x2 greater than equal to 3. So here you will have some point, I guess, somewhere here it is merging. So you will have to solve if x2 is 3, then how much is your x1? Okay. So that would be, if x2 is 3, then x1 is 154 minus 34 into 3 by 18. So that is 2.889. Okay. So that means mostly here only you will be obtaining a solution. So whatever z value you get, and then you will have 2.889 comma 3. Now you will also have to check your z value. If let's say it is greater than or less than the current function, sometimes on the basis of that also you discard the solution. You decide whether to further branch or not. Okay. So let's say if I plug in the values, I'll be getting 7 into how much? 2.889 plus 11 into 3. That is 53.2. Okay, now again, you further branch this. Now, on what basis will you branch? X1 is less than equal to 2 and X1 is greater than equal to 3. So that means, let's say if I take up this one, my model becomes max Z subject to X1 plus X2 less than equal to 6, 18X1 plus 34X2 less than equal to 154, X2 greater than equal to 3, X1 less than equal to 3. So do you understand? You keep adding one constraint at a time. So I would suggest solve this. Okay, this is your homework. Solve
Ma'am,
this.
we always, I had a doubt.
Yeah,
We always choose the lower number in the both, like x1 and x2 value. We had 3.1 and 2.8, so we chose 2.8 because it was the smaller value.
not exactly. I mean, you can also try it out the other way. Okay,
Okay.
arbitrarily you can choose. Okay, there is no such
Okay, so
requirement.
there is no like any order like there. We
No, no.
can choose anyone and work
Yes,
accordingly.
yes, absolutely. Okay. So I would suggest that instead of me doing this entire, because now that you understood the funda, you can do this branch and bound methodology on your own, right? So this is like your homework, and I hope this part was clear to all of you.
Yes,
So now what?
usually. So what if this process continues for a pretty long time and the depth of, say, if
Yes,
we have many decision
yes,
variables?
yes. So the next thing which we will discuss is where do you stop? Okay. Usually this takes a lot of computational effort and time. Okay. So that is why it's not a very sought after method. So the stopping rule is that because branch and bound, as you rightly said, takes so long to provide an optimal solution. So most of these ILP packages, okay, they will allow you to specify a suboptimality tolerance factor. Okay. So tolerance factor, what it does is it allows you to stop once an integer solution is found within some percentage of the global optimal solution or the bound. Okay. So that is your basic stopping rule. So I guess, yeah, that's what I wanted to discuss with you today as of now. So we basically discussed what is an ILP, three types of ILP models, how do you do LP relaxation, what is the difference between integer feasible versus LP feasible, when will you get LP solution, I mean, when will you get an ILP solution, even if you solve it using a traditional LP method? And one of the most important solution approaches, which we discussed, was the branch and bound strategy. Okay. Next thing which we can discuss in the next classes are some of the characteristics of ILP problems and, maybe solve problems. So we will probably jump on to solving a classic knapsack problem in the next class. So tomorrow I will try to take it for uh, more than 2 hours. So I will definitely try from 8 to 10 if that is possible. And yeah, see you tomorrow. So any doubts?
So there is a small typing mistake in the point number 3. So instead of small b, can you make it capital B?
Where?
In the point number 3, wherein you wrote ax is equal to b. So I mean, while writing, you wrote it as small b. I mean, just for the correctness purpose. Where a and capital V all have integer entries, I guess. So it's capital B. Nothing special, but this such that ax is equal to b, and where A and capital B have all integer entries.
Okay, okay, okay.
Yes.
Okay, okay, fine. Yeah.
Thank you so very much. So tomorrow,
Yeah. Tomorrow I will try for taking your class from 8 to 10 o'clock straight. Okay. See, I keep very ambitious plans of, holding the classes at 8 o'clock in the morning, but somehow it gets difficult. But nonetheless, I will try my best. So that tomorrow we'll at least cover this ILP part. And see, to be very honest, even if I'm, giving these lectures and everything, at the end of the day, I believe that you should always go back and solve problems on your own in order to get more clarity. So that part is something that you will have to take care of, and I hope you do. So, okay, I'll just share this. So, I'll just share it to myself as of now. I will mail it to you immediately after this class. So, yep, that's it. Thank you so much. Please
thank you
take
so
care.
much.
Have a happy weekend. Yeah.
Yeah, bye.
Thank you,
Bye.
ma'am.
Thank you.